Did you know that there's a type of battery that cannot explode, unlike the lithium-ion ones? As the world shifts toward renewable energy, the demand for batteries is also increasing. The sun does not always shine and the wind does not always blow. So we need batteries to store and release energy for when we need it. That's where redox flow battery comes in, as it does not prone to explosion like the lithium-ion batteries. To avoid putting you to sleep with the chemistry behind how it works, imagine this. Think of making pour-over coffee. You pour water through coffee grounds and it picks up flavor as it passes. A redox flow battery works similarly. We put electrolytes are pumped through porous electrodes, where chemical reactions occur and release ions. These ions are then exchanged between the electrolytes through a membrane, and energy is either stored or released. But just like with coffee, if the grounds are packed too tightly, water barely flows, and if they are too loose, water rushes through without extracting anything. So the structure of the grounds, or in this case, the electrode, is critical for performance of the battery. That's what Khoi Bui, a student from Orange Coast College, California, worked with Sophia Edgar this summer at Harvard on analyzing how different 3D printed electrode geometries affect how well the electrolyte reacts inside them. We print the electrodes with different shapes, pumped in electrolyte, and use high-resolution 3D imaging to observe where and how intense reactions occurred. These reaction zones appear as tails. Think of them as traces to show how much electrolyte is reacting. I then trained a machine learning model to automatically identify and segment these reaction zones into thousands of images, a task that would have taken days or even weeks to do by hand. From that, we extracted data like tail area or its state of charge to compare the efficiency of different electrode designs. The final goal is just not to identify the tails, but to study how electrode geometries influence the mass transfer behavior systematically, and find the core principles that govern this relationship, which will serve as a stepping stone toward developing optimal electrode structures that can maximize electrolyte utilization while minimizing the flow resistance.